What we're going to look at for the second half of the lesson is the pH scale and some calculations that are associated and key definitions associated with the pH scale. Now you have some experience with the pH scale, and things that would be familiar to you is that it's a range. It shows you a range of the pH and gives you a level of acidity of a solution. Some key points on the scale: if the pH is 7, that's considered a neutral solution. If the pH is less than 7, that's considered an acid. And if the pH is greater than 7, then that is considered a base. Now, when you are studying the pH scale, what pH stands for is actually the power of the hydrogen ion. And what we're doing when we monitor the pH scale is we're actually monitoring the concentration of the H3O plus or the H plus in the solution. So when we look at the scale, the solutions that are most acidic or lowest on the pH scale have the highest concentration of H3O plus. And the entire scale monitors H3O plus concentration, and when we are very high on the pH scale, what that means is that we have a really low concentration of H3O plus. Now, the square brackets that I'm using are very commonly used by chemists to signify concentration. So when I put square brackets and a substance, that means the concentration of that substance. So this is saying the low concentration of H3O plus. Now, because this scale is monitoring the concentration of H3O plus, what we need is a relationship between the pH and the concentration that is derived from the pH scale. The pH scale is actually a logarithmic scale. And many of you have little experience with logs, so what we're going to do is explore the relationship between the concentrations of H3O plus and the pH, and at the same time investigate the idea of what a logarithm is. What we're going to do is we're going to study this range of concentrations of H plus. So if you look at them, all I'm doing is moving the decimal place over 1, and the concentration of H plus is just getting smaller and smaller and smaller as I go down this list. Now what I've done in this second column, and I'll invite you to do, is to rewrite all of these concentrations in the form of 1 times 10 to the negative x. So just basically put these numbers into scientific notation. So for example, this one here, I had to move the decimal place over 7 to the right. So this in scientific notation is 1 times 10 to the negative 7. It would also be really handy for you to have your calculator at this stage. So we're going to look at a couple of examples and learn how to use our calculator in order to solve pH problems. Now, what we're doing here is we are looking at a very large range of concentrations. So I'm looking at 1 mole per liter all the way to 1 times 10 to the negative 14 mole per liter, which is really, 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 really small. Now what we're going to do is we're going to figure out what the log of our concentrations would be. Now, when you have your calculator and you enter log of a number, so if I enter log of 0.1, what I'm asking my calculator to do is to tell me 10 to the what is going to give me that number. So any time you enter log in a number, you're asking your calculator to tell you what 10 needs to be raised to in order to retrieve that number. This is why we put these numbers into scientific notation, because the number 1 is really equivalent to 10 to the 0. So if I want to know the log of 1, I need to know what 10 needs to be raised to in order to give me 1. So 10 needs to be raised to 0. The number 0.1 in scientific notation is 1 times 10 to the negative 1. So in order to retrieve this number, the log of 0.1 is negative 1. The log of 0.01 is negative 2, because 10 to the negative 2 is equal to 0.01, so 10 needs to be raised to the negative 2. You can try it in your calculator. If you take the log, so you press log and then 0.001, you'll see that it responds with a negative 3, because 10 needs to be raised to negative 3, and that's the equivalent number of 0.001. So really, the log of all of these numbers is simply the exponent in my scientific notation. So you might see here a very interesting list of numbers. They're all whole numbers, and they go from 0 to negative 14, which might look like a familiar range of numbers because this is close to, besides the negatives, this is close to what the pH scale gives us. So we're going to work with logarithms, but we're not just going to take the log of the concentration in order to come up with the pH. What we're going to do is we're going to take the negative log of the concentration of H+, and that will give us the pH. So if we take the negatives, all these numbers, what we see is our pH scale. So like I said before, the pH is giving us the power of the hydrogen ion. So it's giving us an indication of the concentration of the hydrogen ions in solution. Now the reason that we study this on a pH scale is, and in a logarithmic scale, is because we can study a really wide range of concentrations on a very simple 14-point scale. And it's much easier for communication, because if you think about communicating with the common public, talking to them about the concentration being 1 times 10 to the negative 10 molar in their local lake, that's not going to have any meaning to them. But when we put these values on a logarithmic scale, people will have a better understanding of what the pH is. Right? They can understand that that means that that is basic, and they can understand that 7 is neutral, and above that is basic, and below that is acidic. Now this covers a really wide range of concentrations, and that's really important to note, because although we might think, oh, we've only moved 1 unit on the pH scale, there's actually a large difference between the concentrations of the H+ ions in the solution. Anytime we're 2 units, so if we move 1 unit on the pH scale, that's a change in concentration of 10 times. So the concentration of 1 mole per liter is 10 times more the concentration of 0.1. And what that means is that if we move 2 units, there's a difference that's 100 times in terms of the molarity of the solution. So we need to be mindful of this, because when we're comparing values on the pH scale, especially if we go back to our lake example, a small change in the pH from 5 to 4 might not seem like a big deal. But if you understand that the concentration is actually 10 times greater in that pH solution of 4, then that's going to be a bigger concern. So let's just do a little bit of a practice here on our calculator. Let's take this example, and we want to know what the log of 0.225 is. So I want you to get that value into your calculator and take the negative of that. So you've got the negative log of 0.225. Now what we want to do is reverse that. So I want to undo the log. The opposite of log is 10 to the power of. So if you do 10 to the power of negative of your answer, see what you get. And what you get is 0.225. So taking the log and 10 to the power of are opposite functions of one another. Let's look at that in action in this table. If we take 10 to the negative pH, so we've got our pH values, and we take 10 to the negative, these values, so 10 to the 0, 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, what we're getting back is our concentration of H+. So what we've essentially done in this discussion is derived two very important formulas. We've derived the formula for calculating the pH, being the negative log of the H+ concentration. And from the pH, if we want to know the H+ concentration, we've looked at the relationship there, which is 10 to the minus pH. So these are two very critical formulas. This gives you a visual of when we're studying logarithms, okay, the difference between two units. Okay, so we talked about this in our previous slide. And there are other logarithm scales when you look at the Richter scale, for example. That's also measured on a logarithmic scale. And again, why we use logarithmic scales is to study a wide range of values on a very simple scale. This diagram here gives you a nice visual of the changing concentration of H+ as we change the pH. So we're going from pH of 0 across to 14. The concentration of H+, written as 10 to the power of the negative pH, so 10 to the 0, 10 to the negative 4. As you can see, as the pH increases, the concentration of the H+ decreases drastically. Now, the thought of there being H+ in the solution no matter what may not be something that you've thought of before. And it's really important to think of solutions as having both H+ and OH- in the solution. What we have when we have an acid is we have a large concentration of H+. And when we have a base, we have a small concentration of H+, which in turn means that we're going to have a large concentration of hydroxide. When we talk about a solution being neutral, oftentimes people will just automatically think that that means that it's not an acid or a base. But what it actually means to be neutral is that the amount of H+ and the amount of OH- in the solution are balanced. They're the same as one another. So in a solution that's neutral, we still have a concentration of H+. It's got a pH of 7. So if we want to know the concentration of the H+, it's 10 to the minus 7. But because it's neutral, that means that it's balanced by the hydroxide in the solution, which is also going to be 10 to the minus 7. Now, although we study the pH scale, it's important for us to also see the relationship with hydroxide and look at a pOH scale. In the lab, we'll always work with pH because the meters that we use will measure the pH, and our indicators are used to measure pH. However, it's important to recognize that there's always hydroxide in the solution, and so we can always study the concentration of hydroxide in the solution in much the same way that we can study the hydrogen ions in solution. So when we look at the hydroxide, we can see the range of concentrations of hydroxide as being exactly the opposite as the range and concentrations of the H plus in the solution. Much like we can calculate the pH of a solution by studying the concentration of the H plus, we'll be able to study the hydroxide concentration by studying the pOH. And essentially, we can put anything into a logarithmic scale. We can take the power of anything. So if we look at the pOH scale, we're simply looking at the power of the hydroxide ion in the solution. And the P of anything is the negative log of that substance. So pOH can be determined by taking the negative log of the concentration of OH minus. And inverting this formula to solve for the hydroxide, using the fact that 10 to the power of is the opposite function of the log, the hydroxide concentration can be determined by taking 10 to the power of the negative pOH. Now this here summarizes when you have the pH, it reminds us whether or not a solution is neutral, acidic, or basic. So when the pH is 7, it's neutral. When it's less than 7, it's acidic. And when it's more than 7, it's basic. We can examine a pOH scale in the same way. So neutral is 7 in the pH scale, as it will be the same in a pOH scale. And what we want to do is look at the relationship. If we think of an acid that has a pH of 6, it has a certain concentration of H+. The concentration of the hydroxide is going to be lower in that solution. And if we look at these scales, when you have a high concentration of hydroxide, you're going to have a low pOH. So the pOH scale is actually the opposite in that a lower pOH is going to be a basic solution and a higher pOH is going to be an acid solution. So if we look at this, we can see, okay, well, if we've got a pH of 6, that's slightly acidic by 1 pH unit. So on the pOH scale, you're going to have a value of 8, so that it is slightly acidic. If we had a pH of 3 and 4 units away from being neutral towards the acid side, so my pOH in this case is going to have to be 11. And if we look at each of these examples, we can see that the sum in all cases of the pH and the pOH is equal to 14. 7 plus 7, 6 plus 8, 3 plus 11. So these scales can be used hand in hand. And the sum of the pH and the sum with the pOH is always going to be 14. Now from this, we can derive another relationship, which is that the concentration of H3O plus times the concentration of OH minus is always equal to 1 times 10 to the negative 14. Let's look back at this chart in order to help us to see that. When we had a neutral solution, that meant that the concentration of H plus and hydroxide were equal, and they were both equal to 10 times 10 to the negative 7. When we multiply these, 10 times 10 to the negative 7 times 10 times 10 to the negative 7, we are left with 10 to the negative 14. Let's choose another point. If we were at pH of 10, that would mean that the concentration of the H plus in the solution is 10 to the minus 10. The pOH is in turn 4, So the concentration in this case of the hydroxide ions in solution is 10 to the minus 4. And again, when we multiply these, we are left with 10 to the negative 14. Okay? And again, we want to rethink what we mean when we say a neutral acid or base solution. A neutral solution is one where the concentrations of the hydroxide and hydronium are equal. An acid solution is simply one where there's more hydronium than there is hydroxide. And for a basic solution, the hydroxide is in a higher concentration. What this is leaving us with is what I'll refer to as the acid-base chemistry toolbox. We have 6 formulas that we've derived related to pH that are going to help us to do a number of calculations.